All right, we're just going to continue now our study of work energy principles. This is section 4-3 in the text, and this is looking at work energy for systems of particles. So we're just going to try to see the effect of dealing with systems of particles with respect to potential energy, for example, and conservative forces. And remember, when we did this before and looked at systems of particles, we, for example, found that the um, forces, the internal forces, could be ignored in systems of particles when we're looking at, for example, the um, velocity and acceleration of the center mass of the system. So the question is whether that kind of approach can be um, used when we do work and energy on a system of particles. That is, can we ignore the internal forces and just focus on external forces? To to give you the bottom line, the answer is no. You have to, when you're doing work and energy, you have to keep the um, internal particles in. So as a kind of a model problem, let's just assume we have a fixed table and we've taken two books, a dynamics book and a materials book, stacked them on top of each other, and tossed them on the table in such a way that they start sliding from left to right. So there's friction between the green book and the table because it's sliding, but also there could be a relative sliding between the dynamics book and the materials book, right? So there could be friction between those two as well. And the question, for example, is if you consider the two books as a system, do you have to to include the force, the internal force, the friction force between the dynamics book and the materials book, the green book and the red book? And the answer is yes, because as you might imagine, the friction between those two produces heat. It reduces the energy of the system in an overall fashion, and so it will reduce the kinetic energy, for example, of the system because you're dissipating the system energy through that frictional force, which is dissipating as heat. And so you can't ignore the friction between these two because it will reduce the overall velocity of the system. But let's work that out. And so suppose we have these two books stacked on top of each other. The free body diagram for the top book has gravity, a normal force between it and the second book, and a friction force acting against the motion. Uh, this is drawn this way, assuming that the the dynamics book is moving faster than the lower book, and so the friction force on the dynamics book acts backwards. If we focus on the free body diagram for this book, there's a normal force between the table and the book, the normal force from the book above it, the gravity on this book, the friction force acting in the opposite direction as this one. This is the friction force between the two books. And then the friction force from the table, if the book is traveling to the right, the friction force but from between the table and the lower book will act to the left. And the real question is, does this friction force FB, the internal force between the two particles that constitute our system, does this affect the kinetic energy of the system? And the answer is yes, and we'll see that. There's a lot of derivation here in the next few slides. I'm going to kind of gloss over it um, because it's just the end result that we're after. So in general, we assume we have an XY coordinate system. We have a particle MI and a particle MJ. There are external forces on each of these particles. They're each traveling through some path, and there's a position vector describing each. There's also an internal force that acts equal and opposite on the two particles that acts between them. You could think of this as this gravitational force between two planets, but there's other types of internal forces, such as this friction force in our book. Okay, so for each particle, we have the external force plus the sum of the internal forces on particle I uh, equals the mass of particle I times acceleration of particle I. If we dot that force with the differential path increment and integrate from point 1 to point 2, then we could just do this. We have an expression like this coming from here, right? So the sum from I equals 1 to n over n particles in our system is the integral over the path of this force term dotted with the path, okay, which we can also write this way. So the total kinetic energy of the system is the sum of the kinetic energies of each of the particles in the system. So we can write the right-hand side of this balance this way, all right? So the sum of this mi dri dot dt dot dri is just a change in kinetic energy and going from point 1 to point 2. So that's pretty straightforward. The left-hand side looks like this, okay? The first term is the work done by the external forces, which looks pretty straightforward. It's just a sum over all these external forces of the work done as the particle goes from point 1 to point 2. Okay. The second term coming from here is the work done by the internal forces. We can write that this way. It's a sum over all the particles plus there's an internal sum over the force on any individual particle from all the other particles, so it's a double sum. And the real question is, does this go to 0? If this term goes to 0, then the work done by the internal particles is 0, and therefore we can ignore it. But the answer is no, that's not true. This term is not in general 0, so the work done by these internal forces does not necessarily sum to 0, and we have to account for it because, as I said before, if there's work done by these internal forces, then quite often it will reduce the total kinetic energy of the system, and it can't be ignored. Okay, and so that's our general result, is when you're doing work and energy, you have to count for both external and internal forces to get things right. Okay, so we can write for a system, T1 plus the work done by external particles, external forces, plus the work done by internal forces equals the final kinetic energy, and these would be totals over all particles. Okay, or similarly, we can break the work done into non-conservative and conservative situations or conservative forces. So T1 plus V1, the initial kinetic plus initial potential energies, plus the work done by non-conservative external forces plus the work done by non-conservative internal forces equals the final potential plus kinetic energy. So let's look at some examples. Here's our first system. It's like a little catapult. So we take a block B, we attach it to a spring, okay, and then we put a rope over this pulley and attach it to block A. If we pull up on block B, stretch the spring, and then let go, block B will be pulled down by both the spring and gravity, and as it goes down, block A will travel up and it'll get launched. All right. So let's assume we have some parameters. Block B weighs 8 kilograms. It's released from rest at 2 meters above the ground. Okay. When it's released, mass A, which is 1 kilogram, is in the position shown, right? So we pull this up to 2 meters. This is at the bottom. We let go, and we see what happens. The spring constant is 40 newtons per meter. And the question is, how fast are B and A going when B just hits the ground? So we model these blocks as particles, and we just need to relate the change in position to the change in speed, and that'll give us our solution. We assume the pulley is fixed, and so the forces on the pulley from whatever it's fixed to don't do any work because the pulley doesn't move, so the dr is 0. The tension in the cord itself is not doing any work other than the work it does on these particles. There's no friction here, so everything's conservative, right? If you wanted to handle friction, you could, but we're going to ignore it for now. So T1 plus V1 is the initial kinetic plus potential energy equals the final. The initial kinetic is the initial kinetic of block A plus the initial kinetic of block B. We assume they're both initially at rest, so that'll turn out to be 0. So T1 is 0. T2 is the final kinetic energy. It's the sum of the kinetic energies of the two particles, just as B gets to the bottom. The string is unstretched at point 2, right? So we assume that when B gets to this bottom of this thing, that it's in an unstretched position. So the final potential energy in the spring is 0. It's unstretched. All right. We take our datum to be here for the potential energy due to gravity. So the initial potential energy is the initial energy stored in the spring, 1/2 kh squared, where h is the initial stretch in the spring that was given to be 2 meters. Then there's the initial height, the massive part, block A times G times the initial height of A, right? Relative to the datum, which turns out to be 0. And then the massive particle B times G times YB1, and that's our 2 meters. Then V2, the final potential energy is the final, depends on the final height of block A plus the final height of block B. All right, now we need to connect the two velocities because the string is assumed to be inextensible, and therefore the velocities of the two particles are not independent. They are dependent on each other. And we let L be the chord's total length, so that's the length of this piece plus the length of this piece. So the length of this piece is this distance here, which is the square root of the sum of the squares of this distance plus this distance, and this distance is L minus YA. And then the distance, the distance right here is just L minus YB. And so since L is a constant, then we can differentiate this with respect to time. The L dt is 0, and the derivative of y and yb are going to be the velocities of block A and B. Okay, so we can write this relationship for the velocities of the two particles, which gives this relationship here. Okay, so now we can relate velocity B to velocity of A, and we really only have one unknown velocity then, and we can go back to our work energy method to solve the problem. Okay, so we can also relate the change in heights using the same equation. And so that gives us a second relationship for the kinematics that we can use to solve. Okay, so combining all the energy equations and the kinetics or kinematics equations give us this rather complicated expression for the velocity of block A just as the spring gets to its unstretched position. And if you work through the math, velocity of block A is about 20 meters per second, and the velocity of block B is about 1.5 meters per second. Okay, and if you do your checks, everything checks out, and it's a pretty good result. Okay, one more. Let's look at this rather complicated pulley system. So we take block A, put it on a frictionless ramp, connect the pulley to it. Then we have a rope that goes over here and connects ultimately to block B. And so block B can slide relative to block A, and there's friction between these. So we just take the system at rest, let go. Block A is heavier, so it wants to slide down this way, and it'll pull block B up that way. Okay? And what we want to understand is the the velocities of the two blocks as a function of time or a position. So we model these two blocks as particles, and we just we can do conservation of energy and both potential and kinetic as long as we include the energy dissipated due to friction. Okay, so if we look at our free body diagram, there's gravity on this block, there's gravity on this block, and if we treat these as a system, then there's a normal force on the system due to the ramp. There's no friction here, remember. If we look at an individual block like this, there's a normal force from between block B and A. There's a force from the spring, there's a friction force, and then there's gravity. So we can look at our conservation, the initial kinetic plus initial potential plus the work done by the internal non-conservative force, that's the friction between the two blocks, is the final kinetic plus the final potential. Okay, the initial kinetic is 1/2 MAVA1 squared, the kinetic of the first block initially plus the kinetic of the second block initially. And then this is the final kinetic energy. And we can find what N, the normal force, is between B and A from here. It's just the perpendicular component of the gravity, since there's no motion perpendicular to that contact surface. The potential, we assume that the blocks are initially at zero potential energy, and the final potential is just the final potential energy of block A plus the final potential energy of block B. And these are just the change in heights, right? So it's the mass of each block times G times the change in height. And XA is this distance here. So delta XA is the distance traveled by block A. And delta XB is the distance traveled parallel to the contact surface of block B. Then we have to look at this pulley system, right? We have all these rope lengths here due to the pulley, and we have to relate those as well. Okay, so that comes from the kinematics. So if we let XA be this distance, XB be this distance, then if we just look at the total length of the rope, we have 3 lengths essentially equal to XA plus 1 length essentially equal to XB, and the sum of those is the total length of the rope, and that's not changing. So if we write L equals 3XA plus 3XB equals a constant, then we differentiate with respect to time, then 3VA equals minus VB, right? Because the time derivative of XA is VA, time derivative of XB is VB. Okay, also 3 times delta XA is minus delta XB. If we just look at the change here, again, the change in L is a constant, so there's no change in the total length. So every change in XA gives you a corresponding change in XB. So, and then if we let the difference between the changes in XA and XB be D, then we conclude that the change in XA is 1/4 of D, and the change in XB is minus 3/4 of D. Okay. Now we can put all this together. So the initial kinetic energy is 0. The final kinetic energy is 1/2 MAVA2 squared plus 1/2 MBVB2 squared, but VB and VA are related, so we can substitute for VA. So now we have the final kinetic energy just in terms of the final velocity of block A. For the kinetic energy, the final kinetic energy, for the potential energy, the final potential energy is 1/4 of 3MB minus MA GD sine theta. That comes from an analysis like this. You write the potential formally and then just convert everything to be a function of d, the difference in the changes in the motion of the two particles. And so you can write your conservation equation, and you can solve for VA2, which is the only unknown left, and we get this rather complicated expression, including the dissipation due to friction. All right. If you put in the numbers, block A is traveling at 0.14 meters per second, and block B is traveling in the opposite direction as it should at 0.427 meters per second. The results dimensionally correct, and things look about right. If A and B were disconnected, then VA2 without the friction would be 0.92, so that's higher than what we would see with the friction. So you can see that the internal force caused dissipation and reduced the total kinetic energy of the system. All right, so that gives you some sense of how you deal with systems of particles.